Hi Vernon, thank you very much for the email back on video, I think it's number 5 or number 6 on separation of variables, where I'm saying we found the kernel, the very crux of what makes the this approach be able to obtain the unified field theory and be able to establish it. As we have, I've usually seen, to be honest with you, Schrodinger's equation, I've usually treated this as a constant, and as a result, as a constant, as I've shown, yes, it will actually separate, and I can go into that in more detail. Just to go over, because I think this is an excellent method to be able to communicate back and forth so that everything is perfectly clear, and now we're both, I think, very, very clearly on the same page. So what we've got is, what I've said is, basically it's not just separation of variables, it's something called uncoupling. I may be able to uncouple the variables, or the functions. I may be able to uncouple functions so that they, in effect, separate, but each of those uncoupled functions may be highly unlinear. They don't necessarily have to be linear. And yes, there are other things with V that may be linear, or they may be able to be uncoupled. Okay, whether they're linear or not, maybe they're not linear and so forth, but they may possibly be uncoupled. So it's the uncoupling that leads to the ability to determine the boundary conditions. So that's really what I'm looking for. So if I have that psi, which is a function of t, x, y, and z, is equal to, we're saying, a function time, which is of time only, a function x times a function x only, function y, capital Y, so function of y only, the function of z is a function of z only. These are now functions that are multiplied, each one being in its own variable. Because of this, we've said psi equals not 0, and t of t cannot equal 0, x of x cannot equal 0, y of y cannot equal 0, and z of z cannot equal 0. I'm using capital letters to denote the function in each of the variables. So these are situations. Now where we're at is, it's a linear operator. Yes, we know that'll divide out. We know this one we can divide out, and I'm just talking the straight mathematics. This one here becomes, if that was a constant, this whole term would be a linear term. And we can discuss linearity, but I'm quite sure you're quite familiar with that. So that if v is not a constant, if v is some function, and what I've seen it just so far, very preliminary, is that this is a function of x, y, z, but is not a function of t. If that is not a function of time, then I can uncouple the time, bring that over, and since this is not a function of time and that's a function of time, then I can start moving into an eigenspace. I can then determine the time-oriented boundary condition, if you like, and the time-oriented eigenvalues over here that would give me that Et equals h, and h nu is equal to the energy. I can get these two functions out of this if v is not a function of time. But if v is a function of x, y, and z, and I can uncouple it, okay, in some way, so that I can divide this out, I can then separate or uncouple each of the spatial coefficients. So that's a situation I think that we're in, and my job now is to start investigating heavily what this is and what this is. And I did go and read Schrodinger's original work on spectral lines, the determination of spectral lines, and from my memory, I'm just using my memory, v at that time I believe he denoted it as a constant, but I could be completely wrong, and it may be that it is some function of space. So far in the literature that I've seen, v does not have a function in time, so I think we're there already. So if we're not, we're closer than we've ever been before, because this is now very significant, and the fact that the Heisenberg uncertainty postulate, or Heisenberg's uncertainty criteria, forms a boundary so that we can't get into certain areas or make measures in certain areas, to me makes complete and total sense. And if we cannot do a measure, if such a concept as a measure is invalid, then we have to leave things such as the field equations, both with Maxwell and with Einstein, that there are regions in which they are not applicable, I'll put it that way. And that's what I'm saying. So I'm saying with here, this, as far as I'm seeing, and I need to do more investigation, my investigation has to be on this last term. And thank you so much for following me this far, and I think that that we're at least clear in understanding that we both recognize the problem.